In simple terms, dark energy is an unknown energy form that impacts the universe on the grandest of scales. But is it actually real? Or is it just a hypothetical theory scientists use to manipulate us? Assuming our current cosmological model, known as the lambda-CDM model, is correct, dark energy makes up a whopping 68% of the universe's total energy. For comparison, dark matter accounts for 26% and ordinary matter, like the stuff that makes up you and me, just 5%. The rest, like neutrinos and photons, are nearly negligible. So when did we first get a hint of dark energy's existence? The first solid evidence came from observing supernovae, specifically type 1a supernovae. These stellar explosions have a constant luminosity, making them excellent cosmic yardsticks. By comparing their distance to their redshift, which shows how fast they're receding, scientists discovered something astonishing. The expansion of the universe isn't slowing down, it's speeding up. Before this, the prevailing thought was that the gravitational pull of matter and energy would gradually slow the universe's expansion. But this observation flipped that idea on its head. Since then, multiple lines of evidence have confirmed the presence of dark energy. But what exactly is dark energy? That's still a puzzle. Although the evidence for dark energy is indirect, it comes from three independent sources. First, let's talk about distance measurements and their relation to redshift. These measurements suggest that the universe has expanded more in the latter half of its life. This accelerated expansion is a key indicator of dark energy's influence. Secondly, there's a theoretical need for a type of additional energy that isn't matter or dark matter to form what we observe as a flat universe. Essentially, the absence of any detectable global curvature implies the presence of dark energy. Lastly, we have measures of large-scale wave patterns of mass density in the universe. These patterns also point towards the existence of dark energy. To reconcile the measured geometry of space with the total amount of matter in the universe, dark energy is needed. Measurements of cosmic microwave background anisotropies indicate that the universe is close to flat. For the shape of the universe to be flat, the mass-energy density must be equal to the critical density. But here's the twist. The total amount of matter, including baryons and dark matter, accounts for only about 30% of this critical density. This discrepancy implies the existence of an additional form of energy to make up the remaining 70%. The Wilkinson Microwave Anisotropy Probe, or WMAP, provided a significant breakthrough. Its 7-year analysis estimated that the universe is made up of 72.8% dark energy, 22.7% dark matter and 4.5% ordinary matter. Later, in 2013, the Planck spacecraft observations of the cosmic microwave background refined these estimates to 68.3% dark energy, 26.8% dark matter, and 4.9% ordinary matter. One pivotal moment was in 1998, when the High-Z supernova search team published observations of type Ia supernovae. Their findings suggested that the expansion of the universe is accelerating. This was followed in 1999 by the supernova Cosmology project, which corroborated these observations. The significance of this discovery was recognized in 2011 when the Nobel Prize in Physics was awarded to Saul Perlmutter, Brian P. Schmidt, and Adam G. Rice for their leadership in this groundbreaking work. Since then, multiple independent sources have corroborated these observations. Measurements of the cosmic microwave background, gravitational lensing, and the large-scale structure of the cosmos, as well as improved measurements of supernovae, have all been consistent with the lambda-CDM model. However, some skeptics argue that the only indications for the existence of dark energy are observations of distance measurements and their associated redshifts. They claim that cosmic microwave background anisotropies and baryon acoustic oscillations merely demonstrate the distances to a given redshift are larger than expected from a dusty Friedmann-Lemaitre universe and the local measured Hubble constant. Despite these debates, supernovae remain invaluable for cosmology. They are excellent standard candles across cosmological distances, allowing researchers to measure the expansion history of the universe. By examining the relationship between the distance to an object and its redshift, scientists can determine how fast it is receding from us. This relationship is roughly linear according to Hubble's law. Measuring redshift is relatively straightforward, but finding the distance to an object poses more challenges. Astronomers use standard candles, objects with known intrinsic brightness or absolute magnitude, to measure distances based on their observed brightness or apparent magnitude. Type Ia supernovae are the best-known standard candles because of their extreme and consistent luminosity. Recent observations of these supernovae are consistent with a universe comprising 71.3% dark energy and 27.4% of a combination of dark matter and baryonic matter. The cosmological constant, usually represented by the Greek letter lambda, is an intrinsic, fundamental energy of space itself. This concept is a cornerstone of the lambda-CDM model. But what does this mean for our understanding of the universe? According to Einstein's theory of general relativity, energy and mass are related through the famous equation E = mc2. This relationship predicts that the energy of empty space, often referred to as vacuum energy, will have a gravitational effect. In essence, even the void of space isn't truly empty. It possesses a form of energy that influences the universe's expansion. However, this seemingly simple explanation brings with it some profound challenges. Quantum field theories predict a cosmological constant that is a staggering 120 orders of magnitude too large. To reconcile this, an almost but not exactly equal term of the opposite sign would need to cancel it out. This is one of the major outstanding problems in modern physics. Some supersymmetric theories take a different stance, requiring a cosmological constant that is exactly zero. This divergence in theories adds another layer of complexity to our understanding of dark energy. In the realm of string theory, the situation is equally puzzling. It remains uncertain whether there exists a metastable vacuum state with a positive cosmological constant. Physicist Ulf Danielsson and colleagues have even conjectured that no such state exists. If true, this would not rule out other models of dark energy, such as quintessence, which could still be compatible with string theory. Let's turn our attention to another fascinating candidate for dark energy, quintessence. In quintessence models of dark energy, the observed acceleration of the universe's expansion is driven by the potential energy of a dynamic field, aptly named the quintessence field. Unlike the cosmological constant, quintessence can vary both in space and time. To avoid clumping and forming structures like matter, the field must be extremely light, possessing a large Compton wavelength. In the simplest scenarios, the quintessence field has a canonical kinetic term, is minimally coupled to gravity, and does not feature higher-order operations in its Lagrangian. As of now, there's no direct evidence of quintessence, nor has it been entirely ruled out. It generally predicts a slightly slower acceleration of the universe's expansion compared to the cosmological constant. Some scientists believe that the best evidence for quintessence would come from violations of Einstein's equivalence principle and variations in fundamental constants over space or time. Scalar fields, predicted by both the standard model of particle physics and string theory, face an analogous challenge to the cosmological constant problem. Renormalization theory suggests that scalar fields should acquire large masses. One intriguing aspect of quintessence is the coincidence problem, which asks why the universe's acceleration began when it did. If it had started earlier, structures like galaxies wouldn't have had time to form, making life as we know it impossible. Proponents of the anthropic principle see this as support for their arguments. However, many quintessence models exhibit tracker behavior, where the quintessence field's density closely tracks but remains less than the radiation density until matter radiation equality, triggering quintessence to behave as dark energy and eventually dominate the universe. In 2004, scientists fitting the evolution of dark energy with cosmological data found that the equation of state might have crossed the cosmological constant boundary, W = 1 from above to below. A no-go theorem proved that this scenario requires models with at least two types of quintessence, known as the quantum scenario.